Today we're going to be working on the right-hand rule practice worksheet, and we're going to work on the induction notes. We're going to start with the right-hand rule practice sheet. This should review skills from Friday, so you should actually be pretty good on this. In this first picture, for example, you can see that we have a compass up here. The compass tells you something about the north and south of this electromagnet, right? So you should be able to tell whether this end of the magnet is either north or south, right? That's the question. If you know that this is north or south, you should be able to wrap your fingers in the direction around the coil so that your thumb either points north if this end is north, or points north if this end is north. So once you've decided which end is north, you will either wrap your hand this way, right? If you do this, that means that you think that the bottom of the magnet, right, the bottom of the electromagnet is north if this is your thumb. I don't know why it's not writing anymore. There we go. And so if this end of if you think north is down, then you want your hand to have your thumb pointing downward, right? So you would have your hand wrapping around the magnet like this, right, with north down here, right? On the other hand, if you think north is up, you should have your thumb pointing upward, right? Oops, that's a bad thumb, but whatever. And then your hand should be coiled this way. So you can actually tell, oops, like this. Okay. If that's the case, right, if north is up, then you would have to have current going such that it wraps around the coil going into the page on the right and out of the page on the left. If your thumb is down, it would go into the page on the left and out of the page on the right. Okay. Either way, your thumb points north. Right? And so you should just look at the compass, choose which end of the magnet is north, and then wrap your hand accordingly so that you can see what direction the current goes. Don't forget that current always runs from plus to minus. Right, from plus to minus. So once you know the direction of the current, you can figure out which end of the battery is which. And so your goal is going to be to figure out if this end, for example, is plus or minus. And that's the question. And then the same for this end. Okay. In question 2, you've got a loop here, right? You're going to write, you've got a plus and a minus on the battery, so you know the direction of current. What I would suggest doing is, here we've got those little circles, right, where we tend to draw X's or dots. So what I would do is draw an arrow here, and the question is, up here, should I draw an arrow going this way for current, or this way for current? One of those two. Once you've decided that, you're going to use your right hand and put your thumb in the direction of current. And then your fingers will wrap around the wire, and you'll either draw an X or a dot, depending on if your fingers are coming out of the page up here. You would draw, if your fingers are coming out of the page up here, you would draw dots in these 3 circles. If your fingers were coming out of the page down here, then you would draw dots in these 3 circles. The other circles would get X's. Okay. So you have to decide which way current is going, and then put your thumb in the direction of current, so that you can have your fingers show you what direction the magnetic field is going. In this last problem, you're going to you're going to label the direction of current in either end, right? And so, for example, I'm going to decide that current is going this way. And you can follow me if you'd like. Yeah. So I'm just choosing. Once I've chosen that, I should be able to figure out which end of the magnet is north. Okay? I should also be able to figure out which end of the battery is positive. So once I've drawn current here, remember, current always goes from plus to minus. So I can label my battery. The other one is that if your right hand goes in if the fingers go in the direction of current, your thumb will go in the direction of north. And so once I've decided that current goes this way, I should be able to wrap my hand around that nail in the direction of current, and my thumb will tell me which end of the nail is north. Okay? And so don't forget, your thumb points north. So now if we pause for a second to go back, if we take a look at this first one, right, let's actually see how we might do this. So let me get rid of my markings to make it less confusing. First of all, the compass, as we've seen, this end is north and this end is south. Well, if that's true, that means that this end of the magnet must be north and this end of the magnet must be south. So if I'm drawing this, I need my thumb pointing straight up. So I need my thumb pointing up, and my fingers, therefore, would be wrapping around this way. Right? And so I would have my hand right in front of me with the thumb up. And this would be my right hand. These are all right hand rules. Right? So I'd have my hand like this. Right? So here's my hand in the same direction where north is my thumb. Well, since my fingers have to curl around this way, current must be coming along the wire this way. It must be coming out of the page here. Dot, 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 and X, X, right, and so forth. And so it must be then coming along the wire this way. If that's true, then this end of the battery must be our negative end, and this end of the battery must be our positive end. Okay? If we keep on going with this is the positive end of the battery. Current always goes out of the wire from positive to negative, so it must be coming around this way. Okay? So current must actually be going counterclockwise in this loop. If it's going counterclockwise, down here, I must have my thumb pointing to the left. That means the back of my right hand is going to be facing towards me, and my fingers will then be curling around this way. And I'll have my hand facing like this. Right? Or the back of your hand is this way. Right? If that's true, then my fingers must be going into the page here. And they must be coming out of the page over here. Well, if that's the case, then I should have X's on this side, because that means into the page, and I should have dots here. Okay? So it's pretty easy to do if you just put your thumb in the direction of current. There's no way to get another direction for each of these. If we look at this one, I drew current going this way. Current has to go from plus to minus, which makes this end of the battery positive. This end of the battery must be negative. Otherwise, current would flow in the opposite direction. Since the wire seems to be going over the top of the nail down here, right, that means that my hand must be pointing, have my fingers, well, current has to be going into the page on this side. And out of the page on this side, based on the direction I drew current. I just chose current randomly. It's going under the nail over here, so it must be coming out of the page here, into the page here, out of the page here, into the page here, and so forth. Well, the only way to get that to happen is if I turn my thumb upside down. If I turn my hand upside down, then I get something that with my thumb pointing downward. And so my right hand would look something like this. With the back of my hand pointing towards me, I would get my right hand pointing this way. And let's see if I can continue. There we go. I can continue onto this side if I want to. Right? And so I would get my hand pointing this way. Right, where the back of my hand is here. And my right hand is pointing down. That's the way your right hand would look, more or less, if your fingers were going into the page on this side and out of the page on this side. I would have my right hand pointing downward. Well, if that's true, my thumb is pointing downward. This end must be north. And this end must be south. Okay. So if this makes sense, if we chose current going to the right here, and it was wrapping around the nail in this direction, then the north end of the magnet would be the pointy part of the nail. Right? Well, we're going to take a look at induction notes now. We're going to skip ahead to induction notes, and we want to take a look at two things that we can do with magnets. One is magnets change the direction of current, and that you may or may not already know, but if you don't, you might have seen it in chemistry class when they talked about electrons. And you might have seen something like this, where they have a what's called a cathode ray tube. And in this case, a cathode ray tube is simply a stream of electrons. And if you look, when they bring the magnet near the stream of electrons, it changes direction. And that's right, and we can take a look at it again. The magnet comes near and the stream of electrons bends away from the magnet. In the old days, we used these streams of electrons for TV tubes. That stream of electrons would hit the front end of your TV, and it would cause it to light up. And every place that stream of electrons hit, you'd get a bright spot in your TV. So old TV tubes were called cathode ray tubes. And the way they steered the beam of electrons was with an electromagnet in the back. Actually, two electromagnets. But they would be able to move that beam of electrons by putting a stronger or weaker magnetic field next to it. Well, let's take a look at what that implies. Let's actually go this way. So if we're looking at motion of charge, we can put charge through a magnetic field, and it turns out that if we apply a current through that magnetic field, it gets pushed sideways. Okay, so this is the thing that turns out to be the hardest part of this, is that if we have a current, right, if the current is going up, right, if current, I should remind you that current is I. If current is going up this way, and we have a magnetic field that's pointing this way, right, then what happens is that the force, that current would get pushed out of the page, right? It would get pushed towards us. There would be a force pushing it out of the page. And so what we'd see is, like if we had a wire, right? Like with a current, a wire. And we ran it between two poles of a magnet. Something like this. So we had our south end over here and our north end over here. Right? That wire would get pushed straight out of the page towards us. Right? And so we could actually move that wire sideways by simply forcing it to go between two poles of a magnet like this. Okay. Anyway, we're going to use this right-hand rule a lot, and in the next 2 weeks. And the mnemonic I have for it is FBI. If you go in order from your middle finger to your pointer finger to your thumb, and just say FBI, it kind of looks like a gun, and FBI people have guns, so maybe that's helpful. There are other ones. I like to think of your thumb as pointing towards yourself when you, right? And I is yourself. Magnets sort of, you can use compasses to tell you where to go. And so pointer fingers are kind of like the compass needle. And then force, I don't know. The middle finger stands for F. Right? Now, if we're practicing this, right, we've got a wire going away from us, straight away from us. And so if I wanted to represent that with a symbol, I would draw a big circle with an X in it for current. Okay? If I have my magnetic field, right, with north up here and south down here, that means the magnetic field is pointing straight down. So I'll draw a straight down arrow for my magnetic field. Since I've only got 3 directions. I've got into the page, out of the page. I've got up, I've got down, and I've got left, and I've got right. Like, let me draw these down here. I've got up, I've got down, I've got left, and I've got right, and I've got out of the page, and I've got into the page. We've already used one of these, right? You see how I've used one of these for the current. I've used one of these for the magnetic field. That means that one of these directions is going to be the force. And so I can actually figure this out by using my right hand. And I'll put my thumb, right, in the direction of current, my pointer finger in the direction of the magnetic field, and then the force will be along my middle finger. If I want my right thumb to point into the page and my right pointer finger to point straight down, I'm going to end up with a picture that looks something like this, where my thumb is pointing this way, right? My pointer finger is pointing straight down, right? And that's going to force my middle finger to point to the left, right? If you use your right hand like this. And then my other 2 fingers, my ring finger and my pinky finger, would be towards me. Okay. So if I wanted this to have it, right? So if I wanted to match this, here's the current, I, it's going into the page, right? Here's the pointer finger, that's the magnetic field, it's pointing south. Magnetic fields always point from north to south. And then here is the force, and it's pushing left. So this wire would suddenly get forced to the left if I put a current into the page, right, through this magnetic field. Right? And this is going to be really useful, right? We can make things that, right, it's not handy to be able to force things to be able to move. 2 things that we're going to talk about in this class that use this, right, are motors, right? Because motors, we put power into a motor, put electric current into a motor, and it turns, it moves, right? A force is exerted. The other one we're going to talk about is speakers, right? Speakers, you put a current through them, and they vibrate back and forth. Motion occurs, and they make sound. So it's another application of this. So we're going to see these in a couple different places, right? But it turns out that we can do a couple different things with this. Actually, tell you what, let's stop here for a second, and let's go back to the practice sheet. Let's practice with using these symbols here and using our right hand. So in the first one, remember, current is your thumb, right? Your pointer finger is the magnetic field, right? and your middle finger is the force. Now if you look at this, I've used up, right? I've got up and down, I've got left and right, and I've got into the page and out of the page. Those are my only choices. Well, I've used these for B, taking care of that with B. That goes into the page. I've used this one for current. And so we know that force either goes left or right. Now if I do this, my pointer finger has to go into the page, right? Because B is my pointer finger. My thumb has to point straight up. The only way to do that with your right hand is to have your pointer finger pointing into the page, right? Your thumb pointing straight up. It's not my best drawing of a thumb, but you get the idea. And that would leave your middle finger, oops, pointing to the left, I believe. Right? And so if I have current going upward and the magnetic field pointing into the page, I would get a force going to the left. And so I would assume that I would have an arrow pointing this way that says F. Okay? And that current should be being pushed left. Now what I'd like you to do is try that with this. In this case I have I and B, but this time I is going in the upward direction. So I've used this point, right? I is taken care of. I've got my left and right taken care of because B is going to the right. That means that F has to either be into the page or out of the page. Those are my only two choices. So F has to be one of these two. And if you think this way, it's a lot easier to solve these problems. Now, in this case, we know our thumb is going to be I and our pointer finger is B. And so you're going to try to match your right hand so that your thumb is pointing upward and your pointer finger is pointing to the right. Then extend your middle finger, and it should either point into the page or out of the page. Okay? So I'm going to leave that for you, and you can practice it and show it to me when I get back tomorrow. Now we're going to try this one more time with this magnet. Okay? Current in this case is going along this wire, and it's going into the page. So which of these symbols means current is going into the page? Current into page. So just circle one, the one that means current is going into the page. Now the magnetic field always goes from north to south, and so we know that the magnetic field always goes from north, right, to south. So you want to circle the symbol that's going to show the direction of the magnetic field. Then you're going to have to draw yourself. It helps, it really does. Or you can use this picture over here. Draw yourself a circle, right? And two arrows, one for current, one for magnet, and one for the force, right? If you draw the current into the page, that should take care of your circle, right? The magnetic field will take care of one of your arrows, and when you put your pointer finger and thumb along those, you'll figure out where the second arrow goes, and that will be the force. Okay, I find it easier to draw the circle and one of the arrows, and the arrows, than to match my hand to the picture. But if you find it easier to put your hand on the picture, go right ahead. Okay, but again, you should be able to put your thumb along the wire in the direction of current. Your pointer finger should go from north to be pointing from north to south, and if you do that, it should be pretty clear what direction the force is going when you extend your middle finger. Okay, but you should already know what your two choices are, okay, for the force. Okay, it's either going to be right, because the current will have taken up the one set of symbols, the magnetic field will have taken up another set of symbols, and the force you only have two choices left for your force. All right, well, let's go back to our induction notes. Sorry, here we go. Okay, it turns out that if I simply pulled a wire through this magnetic field, if I forced the wire to go this way, there's no real difference between forcing a wire and moving charge, right? Because the wire contains all of those charges anyway. So if I push the wire through, that's like a man-made current, okay? Not a battery-made current, but a person-made current. And so I should get the same effect pushing the wire through the magnetic field that I got by applying a current through the magnetic field. Since we already figured out that the wire should get pushed to the left, that should create a moving charge going to the left. And so what we find here is that the big thing here is that if I apply a current, right? If I apply a current sorry about that, I get a force. I do what's called inducing a force. I induce a force. However, on this side, if I apply a force, right, then I induce a current. And right, because it turns out that a moving wire and a current pretty much do the same thing inside a magnetic field. Okay? And that may be sort of out there, but it also goes with Newton's third law. Effectively, if pushing an electron through a field causes the magnet pushes it to the left, then if I push it to the left, the magnet's going to cause a current to go backward along the wire, right? So it's like Newton's third law. The magnet always does sort of reacts to whatever I do with the wire. If I push the wire, it causes a current, and if I apply a current, it causes a force. Okay? It's almost like it works against me. Okay? Now we use the left-hand rule for induced current, right? And you don't have to do it this way, but if we want to use the same FBI system, then we have to use our left hand. And so that's what we're going to do in this class. Induced current, we're going to use our left-hand rule. Okay. We'll still have FBI, where F is down here, B is here, and I is our thumb. But in this case, we're going to be applying the force, which means that it'll be given in the problem, or you're making it happen. B is still the external magnetic field, and don't forget it always points south. Right? And then here is the current that we're going to create, I. And so this is created, or the word is induced. Induced means made happen, right? All right. And then it becomes pretty easy to do because you're just going to use the same old FBI. All right. So actually this is the problem in our practice sheet, so let's go there and let's see how this happens. Okay, so number 7. This is going to be the same pattern, and we'll walk you through it. Okay. So in this case, we have the north on the left, south on the right, and so it says, which of the following symbols shows the direction of the force? Oh, sorry, force is pointing straight down. That one's pretty easy. So the force is pointing straight down, so that's force. Okay. And that means up is not going to be an option, right? The magnetic field goes from north to south. Well, that means that that's going to be right. That's your B field. That means left is not an option. Okay. What direction will the current be? Well, we've only got into and out of the page left, so it's either got to be this or this. Okay. And we can tell by simply taking, right, our hand And since we know that B has to be to the right, that's our pointer finger. Force is down, that's our middle finger, right? And there aren't that many ways. And then our thumb will have to either point out of the page or into the page. If I want my force to go down and my pointer finger to go to the right, with my left, but I have to use my left hand. Oh my gosh. Well, that's going to force me to draw a whole new hand. So it would look something like this. My wrist over here, my thumb would end up pointing, I believe, this way, because my pointer finger has to go, right? I'm using my left hand to point towards that south pole, and right, and so I'm going to have my fingers like this with my middle finger pointing straight down. So if we think of this, here's your thumb, here's your middle finger, so here's B, here is your pointer finger, make it a little more pointy, here's here's B, here's your middle finger, that's F, right? So you've got B and F here, right? Here's your ring finger and pinky finger. Here's the back of your hand, right? And so that means your left thumb, right? Remember, this is the left hand, right? So your left thumb would be the induced current, and that's coming out of the page, right? So I would be coming out of the page. And so we'd get a dot here, right? It would be coming out of the page. And so that would imply that the current would be going this direction in the wire, right? Current would be coming out of the page along that wire towards us. So a powerful idea about this is that I can make electricity by simply forcing a wire to move through a magnetic field. And we're going to find that that turns out to be pretty helpful, right? Why do I care about this? Well, if you think of it, a motor, right, is one of the simplest things that induces motion. Well, the opposite of a motor is going to be a generator. And a generator, you apply a force, right, to turn the generator, and you induce a current. And so that's one of the main applications of induced current, is a generator, because that's how we get electricity for our houses. If you think of it, we burn oil to cause a turbine to turn, to rotate, and it forces a coil through a magnetic field and it makes electricity, right? So power plants simply use different energies, right, to turn a turbine. But that turbine is simply a coil in a magnetic field. And that's the same pretty much for every power plant except for solar. For every other power plant, you've got that same turbine. In wind power, wind turns the turbine. And you have that turbine turning in a magnetic field and generating electricity. In hydroelectric, water turns the crank that moves the turbine through a magnetic field. In nuclear power or oil power or coal power, you burn fuel, which then heats steam, and the steam turns the turbine through a magnetic field, which generates the electricity. So every time we look at this, this turns out to be, whenever you're looking at induced current, you really should be thinking about generators, because that's how we get our electric power. Okay. Another application of this, if speakers are induced motion, microphones are induced current. In the case of a microphone, you simply talk into the microphone and it wiggles a coil of wire back and forth, and that creates an electric current that can go to your recording device or to your amplifier or to whatever you use the signal for. Okay, so microphones and generators are going to be good applications of this. At this point, I think you're good to go. What I'd like you to do is finish up the worksheet. There are a few parts of it that I haven't solved for you. I'd like you to try that on your own, and we'll talk about it tomorrow in class and straighten out any confusions that you have. So I will see you tomorrow.